Hello, everyone. Thank you for joining for today's guest speaker webinar on flexible electronics and the future of devices. I'm Palash Vyas, President at IPC Auburn University chapter. And today we will be taking a deeper look with our guest speaker, Jinesh Narangaparambil, at this exciting and futuristic topic of flexible electronics. So let's get started. So today's agenda is we will be going through introductions of the people associated with the chapter, and after that we will move on to the presentation. After that we will have the live Q&A session where you could get an opportunity to ask questions to our guest speaker. After that we will have a raffle giveaway and closure. So this event will be moderated by Wally, myself, and Aaron. Okay, so and this is our team for the IPC and SMTA student chapters. So Shinwi is the vice president, Duha Ali is treasurer, Seth Maddox as secretary, Athi as social media manager, Arvind Srinivasan as special projects officer, Eli Elkins as undergrad coordinator, and Raj Kiran Akula as our graduate coordinator. Dr. Pradeep Lal is our chapter advisor for SMTA, and Dr. Sadha Masha is our chapter advisor for IPC. So this is basically our team, and like we conduct a lot of events, we go to conferences and stuff like that. So I'll have Wally speak on this more. So Wally, could you expand on what are the benefits of joining student chapters, IPC and SMTA?
Yes, thank you so much, Palash and Aaron. So for the IPC, as far as I know, there is a lot of benefits to be part of the IPC, and also being involved as an active member, as a chapter officer. First of all, like money-wise, IPC is opening up a lot of opportunities for students to apply for scholarships. There's two kinds of scholarships: membership scholarship and leadership scholarship. So if you are part of the IPC and you are an officer, you can apply for these scholarships. And also there is a variety, once you are a member in the IPC, you can have access to some certification classes that you can take and be certified in electronics manufacturing. There's a lot of topics that you can have the opportunity to be certified on them. And also there is also an access to some specific standards that we use extensively during our research. For the knowledge-wise, the IPC has a big library since they host the IPC IPEX, which is a conference, the biggest event that IPC hosts every year. So a lot of people, they came for technical conferences and where they show their work. They can present posters, they can present during technical conferences. And through all these years, IPC had a huge library of like technical conferences that it's available for students or for professionals to consult. And also IPC is well known for the standards, so you can have access to these standards. And I believe if you need any information regarding this, Aaron will be a good person to contact. For career-wise, IPC through all the events during the year is a great opportunity, opens a great opportunities for students to get in touch with professionals during the conferences and the expo. So also there is a huge opportunity through the emerging engineer program. where students, they can get in touch with professionals from the industry and they can have some mentorship related to their field of work. So this is pretty much what we do with the IPC. If you can move to the second slide. Okay. SMTA is another great organization to be part of. SMTA stands for Surface Mount Technology Association. So SMTA has a lot of student chapters as well as professional chapters. And they offer also different networking events based on, local chapters and also national levels. Lately, I've been into SMTA, which is the SMTI International Conference, where you can, meet with people and exchange ideas during the technical conferences and also during the expo. They offer for students two big scholarships. So there is a leadership scholarship called Johannes Stromberg Scholarship, and it's $3,000 worth. And also they offer a research grant scholarship. It's called the Charles Scholarship, which is $8,000. So each year, one student can get this scholarship. There's also different programs. If you go to their calendar, you can find different webinars they host in person, and also sometimes hybrid, sometimes online webinars. There's always something to learn from SMTA. They have also a huge library where you can find different research papers. So it's also a great organization to be part of. So.
All right, thank you, Wally. I would like to say that recently we got the results of IPC scholarship, and a lot of students from our chapter have got selected for that. So I think it's a great opportunity if anybody wants to join our chapter. So please look forward to that. So you'll be muted during the presentation, but you can use the chat feature. And during the Q&A session, you can ask questions using the chat or the Q&A feature. Also, just a heads up, we will be giving 3 Bose headphones to those who ask questions. We will be selecting them randomly. So yeah. So without much further delay, we will move on to our presentation. So our guest speaker today is Jinesh Narangaparambil, who is a doctoral candidate in the mechanical engineering department here at Auburn. Jinesh's PhD is mainly focused on the process development and reliability of flexible electronics. In the past, he has worked as a process engineer for a major automotive company. He has received Best Paper awards for his contribution in flexible electronics at IEEE and ASME conferences. He's also the president of ISA, which is also a very challenging job, and he has to balance his work and extracurricular, which he's doing pretty well. And because of that, he has also got voted for the Student Leader of the Year 2021. So Jinesh, I would like you to take forward from here. I'll stop sharing my screen.
Thank you, Palash, for that great introduction. I'll just start sharing my screen. Okay, is my screen clear?
Yes.
Okay. Hello, everyone. Welcome to this presentation. I am Jinesh Narangaparambil, and I'm working with Dr. Pradeep Lal at Auburn University under Mechanical Engineering Department. I am a part of NSF Cave 3 Electronics Research Center, and it's glad to be here and be presenting my work or showcasing the field which is being booming up and exploring a new way towards the electronics industry. So let's start with flexible electronics and the future of devices. Just to give a brief outline of the topics which I plan to cover in today's presentation, is give a brief idea of what the flexible electronics is, the need for the flexible electronics, the various applications of flexible electronics. When said in flexible electronics, people at times do not connect properly to what exactly flexible electronic field is. So I'll give a lot of examples on what are the applications of flexible electronics, followed by methods for development of FE, the current research aspect in industry or in the universities, what we at CAVE3 are doing in terms of contributing towards the flexible electronics, the future of FE devices, and at the end, I would also try to list down some companies which are working and researching in the field of electronics. The main goal of flexible electronics is more about transforming from a rigid platform to a flexible platform. So as you could see, this is a rigid platform, and the exact same form has been converted into a flexible form factor with similar components being attached to it. And so that's the goal where we want to reach at the end and progress forward. With that, what exactly is flexible electronics? So it is basically attaching or assembling an electronic device on a plastic substrate so that it can be transformed into a bendable, stretchable, or a twistable, or something which can be conformed into a unique shapes. In doing so, the substrates used are not just specific to plastics, but some other versions of that are flex glasses, metal foils, or papers that are being used. So in the current era, till now, the most of the components are in the field of silicon, where it is a rigid board with all the conductive or the dielectric or the components all are in a rigid platform. We are planning to transform into a more flexible form where nanocarbon inks or nanoparticle inks have been introduced with polymer, so that it can be flexible as well as stretchable, and other form factors can be added to it. So that's the goal, and that's where we want to head towards to. Saying that, why is the need for flexible electronics? Everyone wants something which is foldable, can be folded and kept into the pocket, or something which can be rolled on and could be used and could be movable as easy as possible. Humans want everything to be more lightweight. If you could see, all the electronic devices are going in smaller and smaller in size, as well as in more flexible form. So basically, flexible electronics add those or supports that platform where it has flexible form factors, design flexibility, weight reduction to a drastic scale, thin form factors, and followed by many other applicational benefits. This can be also further extended with high reliability and low temperature processes, so that low cost substrates can be inculcated and could be used in the application. Here I wanted to show a very broad application, or show how it can be transferred, or why there is an actual need for it. So if you take an automobile, let's say a mid-sized car, it has 50 or 100 MCUs in the system. And with increasing technology, we are keeping adding additional sensors to it. So to run all the sensors or the MCUs, we want wire harnesses, which is approximately 100 kgs when weighed on, and that's the third largest weight contributor after chassis and engine. So if we can reduce the weight of this wire harnesses by transforming into a more of a flexible form, it's going to affect the car performance drastically, and it's going to be cost efficient, it's going to be performance efficient, it's going to be more reliable. To add on to this, if there are various other applications in the automobile field as well, where a lighting system can be transformed from an housing into a more thin flexible sheet on where there are LEDs being attached, and those have been lighted up using printed traces. So That's why there is a need for flexible electronics, where we could explore more and be more optimized in terms of all the usage factors. In doing so, there are various applications and various channels through which we can explore this field. There is automotive, computing and telecom, consumer goods, military, mobiles, wearables, printed packaging, or water. These are all not limited to this, but these are all the industries which are working and are being applied the flexible electronics field to. One such application is flexible displays. You guys would all be familiar with the Samsungs or many other companies which are coming with a foldable phone. So this foldable phone is more of a contribution of flexible electronics, where there's a flexible display. This is a point where we are trying to show flexible electronics is reaching out into every home as much as possible. On the left hand side, there's a conceptual design which hopefully comes in the future, where there would become automobile displays or dashboards which have a flexible display and all controls on it in a digital platform. This reduces the hardwares to a drastic extent. LG came up with a very cool idea of a foldable OLED TV, where it's a 65-inch TV. And if you could see that this TV gets just folded into a small box. So this is the power of flexible electronics, or the field which we are trying to explore in today's life. There are tremendous other applications, such as flexible lighting. So as I mentioned, and housing transform into a thin film sheet is something going to be very beneficial. There are various companies which are collaborating and building flexible lightings. As of now, we have somewhere over here where we have glass OLEDs with thin film encapsulations, but we totally want to transform into a phase as shown over here, where it is fully flexible. This reduces the cost, it increases the flexibility. It also is unbreakable. There's no as such glass being introduced in this, so it is more flexible and unbreakable. To run these systems, we need cells. So just having circuitries being built on flexible platform is not going to help. So there is extensive research going on in the field of flexible solar cells, where a flexible solar cell can be attached onto the windows of a building, and it should start harvesting energy. And that can be used as a partial energy contributor for the buildings which are running on various electronic systems. Similarly goes with the flexible batteries. There is a lot of new batteries coming up in the form of flexible format, and there are tremendous energy utilization effects which have been studied and are being explored at this point of time. Saying that, all the circuitries or all the system needs to have an IC, and those ICs are currently in a silicon wafer form, in a very more rigid form, and to transform into a more flexible form, we'll have to explore more. So this exploration does not just limit to the substrate, but it also goes forward from there in terms of material characterization, of the ink, because in ICs we need a PN junction. So for building a PN junction, there has been an extensive work been done for like hundreds of years in terms of IC building, which is right now, like we hear like there's an 8 nanometer gate been formed, a 3 nanometer gate, the smallest gate that has been formed, and it's giving so much of power or processing power. To reach that platform, we are started contributing towards the flexible form as well, and we want to reach a point where we could compare rigid and flexible to the same processing power and go on from there. So if an exploration and an achievement in flexible form of an IC would be a great achievement towards the electronic industry, and that's gonna change the total scale or the way the world is looking towards the electronics field. Saying that, there are some applications which are already in the field, such as flexible RFIDs or antennas. There are peel and stick kind of RFID tags which goes on to the clothings and could be used at various applications. Right now, there is limitations in the terms of its performance characteristics. There is a lot of extensive work going on in the field of reaching to a 5G application or the spectrum of 5G, where it could be comparable to today's world technology. As of now, we are exploring more of a 2.1 gigahertz of processing the antenna ranging power. Saying that, humans want less things to carry on and be hands-free. So smart clothing is something which is going to be very helpful in this. So smart clothing includes sensors being attached to the clothing, which could communicate and store data, at the same time process and relate to other devices, which could backtrack and give information to each other. So this is a t-shirt which I saw in one of the Flex conferences which I attended in August. It's the MDO wearable imprinted upon a fatigue test. So this device is acting like a central hub for other sensors and collecting and sending important data to the soldiers to the commanders. So you could see that sensors like temperature sensors, cardio sensors, which can detect pulse rates and additional parameters, if is been included into a smart clothing, it's going to be very helpful, and this is going to reduce a lot of work as well as weight from a soldier's body. It is very implied that reducing the weight from a soldier's body is going to reduce his fatigue as well as increase more about his efficiency. So in general aspect, smart clothing is going to be very beneficial, and this is something which has been worked on and has been implemented in the field as of now. Saying that, flexible electronics also needs to have flexible sensors, and there is a tremendous work going on in the field of flexible sensors. Right now, there are already some of the sensors such as humidity, strain gauge, as well as temperature sensors, which are used in the industry. There are Bluetooth connected antennas which have been printed onto the various conformable devices, which such as mobiles, which are available right now. So those all have printed electronics. Now it is more about transforming them into a flexible form and being used into various applications in the field. Saying that, this example covers most of the things which needs to be there in a circuitry board, such as the sensors and chip. So this is a thin die chip, a battery which is conformable, flexible, an antenna that has been designed so that it can communicate to other parameters or devices. This is one of the reports which I was reading the other day, and I felt this is a very cool, interesting application where it is a flexible image sensor for biometric authentication and vital sign measurements for wearable electronics. So this particular device, if been attached to a human body as a tape or a sticker, it could give you out a tremendous amount of information about a person, and that data could be very beneficial at various aspects in terms of people working in enclosed areas. We are not very sure how their vitals are going on. So this is something which is going to be very beneficial and could be look forward to work and get into the industry. Saying that, human-machine interaction is of utmost care, and health monitoring, safety monitoring processes or robotics are some of the applications where human-machine interactions are going on, and there is a lot of work that has to be done. For this application, there are a lot of demands as well in terms of it needs to be flexible, it needs to be stretchable, it needs to be imperceptible in terms of its reliability, biocompatible, and also self-healable. Because our body or our tissues are stretching at one or the other point. So we do not want the substrates to tear off or lose their contacts and have a negative impact on the application. So we want something which could also be healable. So there's a lot of work going in terms of 3D printing of a self-healable biocompatible materials as a substrate. Saying that, it is also important that this healthcare is being addressed in a various forms and being taken forward in a very serious sense. There are a lot of skin patches which have been worked upon and can be attached onto a human body to collect various data in terms of heart rate or the vitals or how you're breathing and all those parameters. A flexible wireless sensor for monitoring babies in neonatal intensive care units is something which caught my attention recently when I was reading through this. This is going to be a lot efficient in terms of removing all the tangled wires. It is beneficial and very profitable to the doctors who are taking care of. They know that this is the live data they are getting. They do not have to worry about it, do not have to worry about any wires going off. This is a great example which can be applied in the healthcare. Recent times during this COVID, there was a university which came up with a machine, which is a flexible soft device that can be attached to a throat, which continuously measures and interprets coughing and breathing rates in the people with COVID. This is a very vital information which is required for this COVID where this world is fighting with. So applications such like this is very beneficial, and you could see that in a very small and stipulated time, people are coming with various applications. So the applications are not very specific to one or the other smaller areas, but it could be reached out into various forms and various factors. Saying that this applications or this industrial touch needs to be built from somewhere. So this is where I'm trying to show the methods for development of methods for developing the flexible electronics. So there are various printing techniques which are being used in the industry right now, and there are a lot of machinery or techniques which have been recently been advanced and been brought into industry in a new scale. Some of the things which I am trying to showcase, or some of them are like an applications or the companies which have machineries to fulfill these requirements. Initially, it all started with contact printing, where most of the people would be aware of, and screen printing. So it is more about, and substrate has been laid down, and a stencil has been kept, and ink has been deposited, and it's been bladed off, and it gets stick to the substrate, and it is good to go. So this was something which it started with, and now there is tremendous amount of other work which has been done, and various other machineries which are being introduced and been worked on. This is some of the examples of a continuous inkjet printer. This works in the similar fashion as a inkjet printer which we use in the offices. You have a substrate which is a paper, and it's been loaded up. There's a machine which has been given some inputs as a picture or something that needs to be printed out, and depending upon what needs to be printed out, it prints out depending upon various control signals, and this has been developed. One such other example is where I wanted to show this video, which shows you how confined and how easy or how the limits are being pushed in terms of flexible electronics. This is a printing and flexible electronic board, which is a functional board. So this is a conductive silver paste which has been printed, and this one particular system can print various things and can build the whole area, as compared to the current technology where we need various machineries, we need various technologies, we need various system locations for doing a rigid board system. So we are trying to transform from a very multi-accessible point to a very smaller area. So this can be also run on a nanoscale technology. So if you could see that the components were being printed, the traces were being printed, the solder or the ECA were being printed. On top of it, a component has been attached, and then a battery has been attached, and the whole circuit has been built. So this is something where the current world is going on, and one system is building most of the thing. So if we could increase this and go into a larger scale, it's gonna be beneficial in terms of designing, in terms of printing, or in terms of building a whole circuitry in all together. Saying that, there are current researches. I wanted to show what are the current researches going on in this field, and how people are contributing towards this, and what are the various fields which can contribute towards this. In the larger scale, I have already shown that in flex system there are various applicational based things such as displays, energy storage, e-textiles, human interactivity, healthcare, or computation. This, if been split into a more broader aspect, it could also be said in terms of its components, attachments, and also various materials, because the substrate, the ink, and the components that have been attached all plays a vital role, and those are all the things which have been researched on continuously. Because for a particular substrate, you need a particular ink to attach so that it has a proper adhesion, proper wettability. Not just that, it also needs to relate with the binding material, which needs to be connected, and the components can be attached onto the system reliably. So to explore more, it is a looping system. So it is basically an iterative system. You need to start with a conductive ink that needs to be formulated. Once that's been formulated, you need a substrate which can take up that ink. And after that's been done, we need to have a platform which we want to print on. So it also depends which platform we are using. Depending upon which platform we are using, we need to decide what is the ink material we want to use, what is the viscosity of the material that we want to use, and how do you want to dispense that onto the system. So there is a lot of research which is going on and has been built step by step. After this whole thing has been printed, we also need to see to cure that or to sinter that material which has been printed. So for that, there is a various other process parameters: thermal sintering, photonic sintering, plasma sintering, and various other sintering processes. So this is a loop which needs to be followed back and forth in all the steps, and needs to have a finalized, optimized parameter so that can be set as a standard. So there is a lot to be done in terms of the application based to achieve that, in terms of standards to be set up and all those parameters. Saying that, I wanted to show a brief idea of what in terms of surface mount technology is going on. So we have sorters currently and in the past, which has been processed at 240C or 260C. So this needs to have a substrate which can sustain that high temperature. So there's a lot of work that has been done, but now in terms of transforming into a flexible field, we want to have a process which can go down to as low as 150C. So currently there are materials which can take up 200C processing, which can accommodate substrates like polyimide or PET films. But there is a lot more improvement required in terms of material characterization and building of a new material. So there is a lot of exploration in terms of low temperature solder or ultra low temperature solder, which there's an extensive research going on, and people are saying that a material or a solder can be reflowed and could be attached to a component at 150C or less than 150C. So there is a huge material requirement in terms of material characterization or building a new material to achieve this platform. So there's a lot of work going in this field as well. Saying that, we at CAVE at Auburn University are also doing a lot of work, extensive work in the field of flexible electronics. These are some of the machineries which we have, and not limited to this. There are some other machineries as well, but just wanted to show an idea of what machineries are. So this is a tabletop machine. So it's just a small tabletop machine, and it can print various devices on it, or test vehicles on it. So this is one of the test vehicles which we printed. So it is starting from how we want to print. So if we want to print these trace lines, we want to define what it should have its trace width as. So for that, there is a lot of process parameters that needs to be learned on different machineries. There is a different process parameters. There are pressure at which we want to print. There is pulse rate at which we want to print. There can be a speed at which you want to move your table. So all those parameters need to be iteratively solved to reach to a point where we are having a defined trace width been printed. After that's been done, there's a lot of sintering process been done in terms of to see how it is electrically performing, how it is mechanically performing, because we do not want it to fail at points where it is bending and it is failing, or twisting and it is failing. So we want to make sure that in all the characteristics performance it can sustain. For this, we do electrical performance, mechanical performance, optical analysis, and SEM analysis. So we want to make sure that the system is reliable and could be used into the application. So for doing that, we also try to compare our data with the actual human body motion. So me and my colleague worked on taking some data on human body motion, where a human body is being subjected to various sensors, 4 sensors. Those motions are being recorded and seen that what is the amount of angle that a human body takes up when it is walking or squatting or jumping or running. So those various forms of movements were being captured, and then that data of angle deformation is being converted into an experimental application, and where we see that there is a data recorded, and we see that how it can be connected, and the life of the test vehicle can be predicted. So there's a lot of information that needs to be debugged and can be attached in terms of how we want to achieve this platform. But this is something which we are doing in field of the flexible electronics. Saying that, we have also gone forward with some of the applications such as component attachment. So you could see that this is a commercially available component, and we got this component and got it disassembled and got it transformed into a design where it can be printed into a flexible form. So a 2 or a 3 board, rigid board, has been transformed into a 5 mil thickness flexible substrate. So this is a big achievement, and in terms of its performance, we could see that it is performing well and is been correlating well with the actually available components at this point of time. So this was more of a 1-layer system where components have been attached. We wanted to explore more and build something which is can be applied in the actual life. So a multi-layer rigid board or a PCB is something which we were aiming to. So for that, we also had designed a flexible PCB in which is functional. So it has ICs, it has passive components like resistors and capacitors, it has LEDs, and this is a multi-layer section. So if you could see in here, there are various junctions, and at those junctions we have connections through micro vias. So we are building multi-layer, but at the same time want to see if this works. So this is a small video which I wanted to show. If you could see, this LED is blinking. So this is a functional flex PCB. By giving some amount of power, we are able to run that system. So we are trying to show that using an ECA or a solder, the components can be attached and a flexible form can be something which we can explore. Saying that, the future of electronics by flexible electronics, there are already some applications which are currently going on, and there is a lot more that has been explored right now. So this is just in a washing machine where the backboard or the circuitry which is running behind this which is really flexible. So we are removing all the rigid or the boxes, heavy boxes, or which takes up a lot of spaces into a more confined things, and this could explore a different arena for the exploration. This is a building which is a conceptual thing where we can have solar cells on it, and it could take and harvest a lot of energy from this. So in terms of how the flexible electronics is exploring or going up in the various markets, so I've tried to show a graph where which resembles the same, where consumer electronics is booming, and this is all of an exponential curve where it is exploring in a large scale. A lot of devices are being explored in this form. In terms of more conceptual thing, we never know. As we see in the the movies, there could be some possible applications where we have a flexible form of pad where we have, instead of the tabs which we have more a flexible form of it. So this is something which is more advanced and a conceptual thing which we would really like to target to. So in here, it's a norm glasses by human capable. This is an AR pair glasses which will allow the users to make phone calls, read text messages, and reply to incoming messages hands-free. So this is a really new technology which we are trying to explore and find a way to achieve this. In terms of healthcare, it's really taking up, and the industry is really exploring in that field. This is one of the sensors which is NSF is working on, where this is just a sticker which can be taped onto a human body with so many other sensors and wireless antennas, ECGs, wireless power coils, and all those elements which can be itself a device. And this is as small as like a 2 mm sticker. There was one more interesting which caught my eye is an application where this is a demo rabbit heart which they are trying to replicate and have flexible sheet on it and see if they can record the heart rates or the muscle movements of the heart and try to take those data and explore the ways to have medical treatment to it through electrical connections. Saying that, this is my last slide where I wanted to show that the industry is booming up and the industry is really taking it this seriously and moving forward to it. Not just manufacturing industries relating to materials, industries relating to manufacturing, industries relating to automobiles, to healthcare, all those fields which can be possible are taking up this task and moving forward in this flexible field of electronics. Saying that, I would like to thank thank IPC and SMTA to give me an opportunity to give a presentation over here on flexible electronics. I've tried to list down my contact details, and I'm happy to take any questions from here. Thank you.
Thank you so much, Jinesh. That was a great presentation. It was so fascinating to see that flexible electronics has such wide variety of applications and also the level of research that is going into development of flexible electronics. It's simply fascinating. So we will move on to the Q&A session. So I'll start sharing my screen. Right, can you see my screen?
Yes.
All right. So, we have a few questions. So let me start off by taking the first question. So Brynmoy is asking, Brynmoy is saying, thanks for the good presentation. And what do you think are the current challenges in the field of flexible electronics research?
That's a very good question, and that's something which I've not added into this presentation because of the time. But yes, so in terms of the current challenges, there's a lot of challenges going on in terms of we already have, let's say, copper or silver, which has a resistivity which has been achieved, and we as of now with the printed techniques are having a higher resistivity than the actual wires which we have. This also includes that we are going to have higher power being consumed in terms of any applications. So that's something which the field is working towards to reduce the resistivity and have various materials being explored so that we can reach a point where it is in comparison 1:1 comparison in terms of power as well. So in terms of printing or in terms of a component being explored, there's a lot of factors in terms of component attachment as well, where there are a lot of challenges of going down to a very small scale or a very low temperature materials which needs to be explored at this point of time. I hope I answered those questions.
Next question is from Madhu Kasturi. So he's asking, is it possible to have application of 3D printed technology for flexible electronics?
Yes, yeah, like 3D printing. So one of the videos which I showed and here was an application of 3D printing in the flexible electronics. So there is a lot of application of 3D printing in terms of printing and substrate, or in terms of printing and conductive traces, or in terms of printing and solder or an ECA. So all those things which can be built in the flexible forms can be possible using a 3D printing technology. Yes.
Awesome. So next question is from Bruce Jameson. He's asking, have they been able to make internal human body flexible devices like the rabbit heart?
I would say no as of now on human body, but there is an extensive research going on the animals body tissues internally been attached onto the brain or on the heart to get those data. So yes, there is an way we are trying to explore to attach the components onto an human body flexible devices. Yeah, but as of now, no. Yeah.
Right. So next question is from David Hollinger. He's asking, you mentioned tests to ensure good electrical and mechanical performance. What tests do you perform to make sure the flexible electronics has good biocompatibility on a person?
Okay, so in terms of what I would address them in two ways. So first is we address the electrical and mechanical performances depending upon what we print at different scalable temperatures and time. And in terms of biocompatibility, we try to have a substrate which is biocompatible, because the printed traces or printed elements are going to be more conductive, and that means it isn't going to be a metal. So not something which we want to have, but yeah, partial of it is being checked for its biocompatibility in terms of its substrate.
All right. So next question is from Suhas Sudhir Bharadwaj. He's saying, thank you for the insightful presentation. Looks like a lot of effort is going towards changing electronics from rigid to flexible form. Are the current flexible electronics development methods such as contact, non-contact printing able to produce them at scale? What is the rate at which flexible electronics manufacturing methods are progressing? And when will flexible electronics become commonplace in everyday devices? That's
a very good question. So in terms of scalability, yes, it is currently a point where we are everyone is trying to explore and see in a small scale, and by maybe next 5 years you could see something which is going to be in a very large scale. Now, as I mentioned, like the mobile industry or the electronics in terms of mobile, we already have flexible displays, so that's already into a large scale market. But yeah, there are some healthcare related applications or devices which needs to still come into that scale, and it's been still in a testing phase. So if to be predicted from the statistics, it's not too far, but it should be something which we will be able to see in next 5 to 10 years. And in terms of what is the rate at which FE manufacturing methods are progressing, the industry is just giving everything towards this field. Every company has a different allotted section for flexible electronics to be explored. So there is a lot of work, and in a faster rate, the progress that has been going on. And in terms of it getting in a flexible commonplace, it's already common to a point where we are trying to see various applications. Like one of them which I showed was the machineries or the washing machine, which has a flexible platform in it. I hope I answered most of your question.
So our next question is from Jimit Patel. He's asking, is there any major difference between rigid electronic testing and flexible electronic testing for failures?
There are some additional tests which needs to be done in terms of flexible electronics, because it's so conformable or it's so flexible. There needs to be a lot of testing that needs to be done in terms of how steady it can be and at various form factors, because in rigid we never try to twist it or bend it or fold it, but in terms of flexible, those are some of the additional testing methods which needs to be inculcated to check for its failure capacity.
All right. So next question is from Kais. He's asking, what reliability tests should be performed to make sure the flexible electronics are within standards?
Why is it a challenge? Because there is no set marks. I mean, we are trying to explore a field which is not something which is being generally done. So there are a lot of challenges which are coming up in terms of its application. It needs to be something which needs to be flexible. At the same time, it needs to be reliable enough to go onto a human body, or let's say. So there are additional parameters which are coming up when we are introducing a whole new factor into it. From a 2D factor to we are going to a 3D or a more 4D system where the things are being twisted, turned, and so there are a lot of additional challenges coming up and more additional standards that needs to be set up.
All right, so we'll just take maybe a couple of more questions and that's it. So Aarti is asking, can you please share some of the applications of flexible electronics in aerospace applications or in harsh environments, similar harsh environments?
Yes, so there are a lot of work going on with printing flexible, so having circuits which have been flexible and could be attached or been taped onto a circuitry. So the automobile applications are also being taken up into an aerospace applications where the circuitries are being transformed from a rigid to a flexible board. But in terms of harsh environment, the material aspect comes into picture where carbon nanotubes is something which has been explored at this point of time. And for high temperature applications, that's something which is going to be workable, and that's something which has been explored. So there's a research going on where the circuitry has been built and been attached onto the panel of an aeroplane and been addressed with 1000 degrees Celsius of temperature. So that's an harsh environment application, and the material which is used in it is carbon nanotubes. So yes, there are a lot of applications in aerospace, which is also similar to automobiles. The only thing which is an additional challenge is the materials that needs to be used and the reliability that needs to be achieved in those applications of harsh environment.
Okay, we'll take just one last question, Jinesh. This is from Dylan Grace. I know you mentioned flexible PN junctions briefly. Do you think flexible ICs and CMOS will at some point become as important for smaller nanoscale electronics as flexible print surfaces are?
Yes, yes. I mean, that's where the community is trying to head towards. where we can have a CMOS or a PMOS system, and that could be introduced into the actual circuitry and could be used in a more flexible form. So as I mentioned, there's a lot of work going on, but the exploration is still not to a point where it can be used. So if we can reach a point where we have materials being explored and could be deposited into a PMOS or a CMOS system, that's going to open up a whole new lot of in field application in this industry.
All right, there was a lot of questions, Jinesh.
I'm happy and I'm glad to be here, and I hope I have answered almost everyone's question and properly. Yeah.
Yeah. All right. So let me move on. So we have taken note of all the people who have asked questions, and we will randomly select three of y'all, and you should receive an email if you have been selected by the end of the day. So please watch out for that. All right. So we are at the end of our today's session. So Jinesh, that was a really insightful presentation. Seriously, I myself did not know a lot about this topic, but today I feel like it's so interesting, and it's the future of electronics. So it has cleared a lot of questions for me as well. So thank you so much. I would like to thank firstly Aaron and the IPC committee who have played a huge role in organizing this. Also, thank you to Wally and my team members who have worked behind the scenes to make this success. And last but not the least, thank you to our participants, without whom this would not have been possible. So you have any closing remarks, Jinesh?
Thank you for inviting me, and I hope I have given some amount of insight towards this field and have introduced an crazy idea into you guys so that you can explore more and explore more towards this field. And thank you IPC and SMTA chapters from Auburn University to give me a platform to present. And yeah, I look forward to connecting with you guys soon. Thank you.
Sure. Thank you so much. Thank you everyone for attending.